In this video, for Module 16, we consider overland flow and streamflow. Well, let's start with some definitions. I think most people are familiar with what a valley is. So we have our valley bottom location shown here and the valley side. But perhaps a term that's less familiar with you is interfluve. And interfluve is the high point or high points between valleys. So here we see some interfluves in the distance here that separate valleys. And then we have the valley lip or valley rim, which is the side of the interfluve. So what exactly happens to precipitation after it falls? We know that it can be intercepted or it can run off the surface. So interception is interception by trees, grass, or crops. And as noted here, vegetation can intercept up to 50% of rain that falls. But what isn't intercepted by vegetation runs off the land surface as surface runoff. Now let's take a look at some terms that are used to describe surface runoff. Now when things are somewhat unorganized, let's say during a rainstorm, you're standing outside, it's raining, water is sort of pooling up, forming puddles, and it's kind of flowing over the surface in an unorganized way, we call that overland flow. And when things get organized, when water from overland flow begins to settle down in low areas and flow regularly, we call it stream flow. So a stream is generally something that's flowing all the time, although there's some exceptions that we'll talk about. Let's talk a little bit about erosion by overland flow, and we'll begin with splash erosion. So we know splash erosion is where droplets of water are hitting sometimes unconsolidated material like sand or dirt that isn't that's located in a non-vegetated area. Here's sort of an example of what we're talking about in terms of the impact of splash erosion. Here we see droplets of water falling and material sort of sent off in all directions. And if a drop of water falls on relatively level ground, we see that when those materials are sort of pushed up and sprayed in different directions, they're sort of sprayed evenly. However, when a droplet of water hits a slope, more material is pushed downslope than upslope. Sheet erosion is where you have a larger amount of water involved that sort of kind of just covers the land surface like a sheet. And of course, it's a more effective at eroding materials and carrying materials away. So this is an example of sheet erosion on a field. And then rill erosion happens when, as the water passes over materials, it picks up the smaller materials and carries those materials away. They're generally lighter and more easily transported. So rill erosion, you see the beginnings of small rills that form in the land surface, especially places that aren't covered with vegetation. And then finally, where things get pretty extreme, we call it gully erosion. So deeper channels begin to form. Let's talk a little bit about erosion by stream flow. So in comparison to overland flow, stream flow is much more effective in terms of moving materials, and it has to do with the amount of water involved. So much more water. We know that the velocity of a stream depends to some extent on its gradient. So a steeper slope is going to produce faster water flow, and that makes sense. We know another factor that determines the erosive effectiveness of a stream is turbulence. So turbulence is water that's sort of flowing other than in a straight direction. So turbulence can be greater where you have rocks and debris, things that are sticking up in the bottom of a river. And you tend to have less turbulence when you have a smooth bottom. And then the resistance of rock also plays a role. So really tough rock, like in this video, is not going to be as resistant to erosion. So if you have softer materials like sandstones, those are more easily carried away, but harder rock like granite, for example, is much more resistant to overland flow and stream flow. Let's talk a little bit about transportation by stream flow. We know that fast-moving streams carry material in two ways, as suspended load and as bed load. So what's the difference? Well, suspended load, as you see in this picture with this dory, the water looks kind of chocolatey almost. That's because the water is carrying that fast-moving water is just picking up sand and silt in particular, and some particles of clay as well, and incorporating those particles just in the movement, just carrying those particles along just by the moving water. So it looks very, very turbid or sort of chocolatey. Then the bed load is where bigger materials are kind of roll or slide along the bottom, and we'll look at that in just a second. The slower moving streams transport materials primarily as bedload only. So they kind of roll things and slide things across the bottom of the stream, and it happens very, very slowly. Let's take a look at the same exact stream, but two views of the same exact stream. On the left, the stream when it's carrying more water. We see quite a bit of material carried as suspended load, so just by the movement of the water, and also as bed load. And then on the right, we see bed load only, so only the bigger materials that are just sort of rolling very slowly along the bottom, or they're sort of skipping along the bottom, but there's not nearly as much material being carried. And here you see in these containers the turbidity that's associated with suspended load as opposed to the turbidity with bed load, and it's the water is much clearer in the case of a slow-moving stream that's carrying materials by bed load only. Here's a hydrologist sampling suspended load in the Little Colorado River, and he's got these look like milk jugs where he's sampling water in different places in the river. So how exactly does material move in bedload? Well, we have a couple of different ways that material moves in bedload. As saltation, where particles of like the size of small pebbles will sort of bounce along the bottom of the stream bed. They'll be picked up, maybe carried for a meter or so, and then set back down, picked up again, set back down. So they sort of bounce along the bottom. And then in other cases, the bigger chunks may move very slowly through traction. I've sort of accelerated things here a little bit, but even this big boulder, you see looks like a kayak about to sort of shoot a little area of rapids. Even this big boulder can move over time. The materials underneath it may be removed by fast-moving water, and this thing may take a slow turn. It may just make, just sort of roll over once in a very long period of time. So very slowly, even big materials can move downstream in this process of traction. Call this a smart rock. This is actually a rock that has a tag that's been attached to it so that hydrologists can study the movement of the rock downstream. So they use radio tracking. So it's sort of crazy to think that we would tag a rock, but that's a way of keeping track of the movement of some bigger particles as part of the bedload. Just to show you this cutaway view, this profile of a river stream shows you two different points in time. In the upper example here, you can see that more recently the stream that was here carried bigger pieces as bedload, but some time before that, a lot of the movement of material was carried as suspended load. So probably at some point in the past, the river that was here was moving more rapidly, had more rapid movement of water, and then for a period of time, the water that was carried may have been diminished, so that most of the material carried was through bedload. We use the term alluvium as a generic term to describe materials that are carried by rivers. So alluvium is just sediment that's carried by, just a generic term for sediment that's carried that refers to anything that a river carries. Now, we use this term deposition to describe materials that have been transported and are left behind. So in that last slide where we were looking at some of those rocks and smaller sediments, that's deposition. So you start with erosion, so you have to remove a material, and then you transport it, then it gets left behind through deposition. So a good example of a coastal landform that's an example of deposition is a beach. So a beach is there often because a river comes out along a coastline and carrying sediment, sand, silt, and clay, and some of that sand, silt, and clay, particularly the sand, is deposited and left behind. So that's a depositional landform. So here we see sort of a relationship in this graph between particle diameter, referring to particle size in millimeters, and stream velocity along the other axis, the y-axis. And we see that when stream velocity is very high, just about everything is moved. So erosion is taking place, materials are picked up and carried away. Transportation happens where you have perhaps a little bit lower stream velocity, things are carried along, maybe not new stuff being eroded, but just existing stuff is just transported. And then where stream velocity starts to decline a little bit, and by the way, this is in cubic centimeters per second, a deposition takes form. So we have slower moving streams. Stuff may be left behind. So here we see in these two videos a faster moving stream that might represent where erosion is dominating, where material is being removed all the time, and then a slower moving stream which might result in some materials that are sort of pushed out of the way and left behind through deposition. So some factors that are important in shaping rivers. One is the length of geologic time, and you might recognize this picture. This is from Artist Point in Yellowstone National Park, pretty famous place. Also shown in a lot of Thomas Moran paintings. This is the Grand Canyon of the Yellowstone, a pretty scenic place. Not to be confused with the Grand Canyon. So this is the Grand Canyon of the Yellowstone River in Yellowstone National Park in Wyoming. But the length of geologic time is a very important factor. So it just takes a long time for rivers to shape places and certainly to cut down through these different layers of sediment. So length of geologic time is one, and then the work of floods is a second factor. Here's an example of the idea of length of geologic time. Here's the other Grand Canyon, the Grand Canyon in Arizona that was formed over millions of years as the Colorado River cut down at the same time that these layers of sedimentary rock were pushing upwards. So I always liken it to a knife cutting down through a pat of butter that you're pushing up. So you're pushing up on this pat of butter as this knife slices downward, but it takes a long time. Okay, a little bit about floods. We know that floods happen where you have meandering rivers, and here is a river that is in its normal channel between two bluffs. We see two bluffs right here, and then where the river reaches flood stage, the water expands out to the bluffs. And how often do floods occur? Well, we can say that it's hard to predict exactly when floods occur. If you are buying property or like in a housing division or even in the country, you might be familiar with the term 100-year floodplain. That is an area that on average floods every 100 years. What a 100-year floodplain doesn't really tell you is exactly when the flood will take place, because no one really knows. It could happen in 2 successive years. So a 100-year floodplain is the area that floods an average of every 100 years. A 10-year floodplain, an average of every 10 years, and so on. Here's the Wabash River in Indiana at flood stage, and just to show you how often these floods, in terms of discharge, these are the bigger floods are shown here at the top right of this graph, but this is the reoccurrence interval in years. So we have those bigger floods with higher amounts of discharge. Discharge refers to the amount of water. This is in cubic meters per second, so those really big floods are not happening as often. So some impacts of floods. Let's talk about them briefly. We know flooding can happen associated with hurricanes. This is in southeastern Minnesota. This is not hurricane flooding, but it does happen when there's heavy rains. This flooding was associated with hurricane development in Houston. So some high water in Houston, flooded areas, really terrible conditions for Houston back in 2017. Some homes that were damaged in a big way. Flooding along the Mississippi River. Mississippi River floods out to much wider, so that's much wider in places. I can recall the Mississippi River being more than 2 miles wide in some places, and when I've crossed it, the Mississippi River does experience flood stage occasionally. Here's some flooding in a small town in Austria along a river. So it doesn't just happen in flat areas, it happens in more mountainous areas as well. And we know that weather fatalities tell us that if you compare some natural disasters like hurricanes, tornadoes, lightning, this is the average number of fatalities per year, floods are the big one in terms of loss of life. And I like to apply this idea. If you hear this term, don't drive through, or you hear people say don't drive through low areas during heavy rains when you might experience flooding, so turn around rather than drive through. Here's sort of something that may illustrate that. I call this why it's a bad idea to drive into floodwaters and other tales. So here we have a car. What we're going to do is we're going to say that water weighs 62 pounds per cubic foot. So we can say when a vehicle stalls, when it drives into or through a low area, the water that may be moving in the river or stream is transferred against the side of the car. So you might think, well, what can that really do? Well, it can create a buoyancy. So the buoyancy is the biggest factor. The car weighs 1,500 pounds less with each foot of water and begins to be transported, perhaps downstream, something that would not be a very welcome sight. And here's a little video here so you can sort of see that, somebody attempting to cross a flooded low point in a roadway. So just don't do it. Just turn around and live. Some mitigating impacts of floods. So some things that we can do to try to lesser the impact of floods. Here's some volunteers that have come together in Memphis to deal with the rising level of the Mississippi River. Filling sandbags. You can purchase things like this, the flood shield. I'm not sure how effective they really are, but if you have water that's rising rapidly and then perhaps drops quickly, the flood shield might help some of the water, or help to prevent some of the water from entering your home. I put together this graph so you can sort of imagine how floodplain development is managed. So we know if you live in an area of flood, that's where floods happen frequently, the very lowest lands that are closest to, or I guess you could say most susceptible to flooding, are oftentimes going to be restricted. So here in this example, we see these low-lying areas that have a high flood risk are zoned for agriculture, recreation, open space, commercial, things that won't be damaged as badly. So as the floodwaters rise, here's our rising floodwaters here for the 25-year floodplain. Areas that are high flood risk, well, maybe you would still build, depending. So flood-resistant two-story high-rise residential, industrial, commercial, those areas are still at risk and may lie within the 50-year floodplain, or the place that floods on average every 50 years. And then we have, for moderate risk, the 500-year floodplain. Those are pretty rare to have floods in those areas, but it may flood. And then areas that are a little bit even higher, the 1,000-year floodplain, single-story houses, so it may be safe to build in those areas. And then no flood risk, you'd probably want your critical utilities, hospitals, evacuation centers, other things that are really critical. That you'd want to site those places in areas that have no flood risk. So one question that comes up occasionally is, what can you do? What else can you do? Well, you can build artificial levees to protect your property. So here's sort of a cutaway view of an artificial levee. So we see a levee means just a high point around an area like a river or a lake to prevent flooding, more often along a river, a natural river. So one of the things that makes artificial levees controversial is when you build them, you prevent flooding in your area, but you actually contribute to the possibility of flooding that's even worse downstream from your location. And here's a couple of views of the work of artificial levees in protecting land. This one didn't work so well, at least on the left-hand side. On the right-hand side, it seems to have worked okay. Here's another one that gave way along the Mississippi River, and you can see it flooded into this area on the right-hand side of the photograph. But as I mentioned, where artificial levees are built, they may actually contribute to some extent to flooding downstream, because that water has to go somewhere. So that water that would normally flood into, say, areas that would be used for recreation or open space, if you prevent the water from going into those areas, it's going to end up becoming, the flooding was going to be a little bit worse downstream. It's not a reason to avoid building artificial levees, but it's just something to be aware of. And I like the picture of this guy here in his house. He has this levee. He is just, or she is just bound and determined that the flooding isn't going to affect this particular piece of property.